All right, in 7.7 part 2, we're going to take a look at de Malvere's theorem. So this just allows us to raise a complex number in polar form to a power, right? So we're saying that our complex number is in this form, and r times the cosine of theta plus I times the sine of theta. So to raise a number like that to any integer power, I raise r to that power, but then I just multiply the angle times the end value. Okay, so let's go through a few examples of how to do something like this. Okay, so let's say that our z, our complex number, is 1 plus I. Well, to use this theorem, we need to put that number into polar form. So first, we need to convert. Right? We need to find r. Okay, so we said to find r, we take the square root of a squared plus b squared. So that would just be the square root of 1 squared plus 1 squared, which is just the square root of 1 plus 1, which will be the square root of 2. And then we need to find theta. So to do that, we found the reference angle, right? So we said we want to find the inverse tangent of the absolute value of b over a. Okay, so b over a would just be 1 over 1, which would be the inverse tangent of 1. And if we put that in the calculator or think about, where on the unit circle is tangent equal to 1, well, that's going to be at pi over 4, square root of 2 over 2 over the square root of 2 over 2. So we can say that occurs at 45 degrees, right? Now, remember, this is our reference angle. I should have, right? That's our reference angle. So now we still need to think about, well, what quadrant is this in? So if we think, well, 1i is going to be in the first quadrant. So that actually means that this angle here will be 45 degrees. So the reference angle and our actual angle end up being the same thing here. Okay, so my complex number is this. All right, so now I can raise this to a power. First, we want to raise it to the 16th power. So z to the 16th power is going to be the square root of 2 to the 16th power times the cosine of 16 times 45 degrees plus I times the sine of 16 times 45 degrees. Okay, and then we can simplify, right? So the square root of 2 to the 16th power, right? We could put that in the calculator, or we could think, well, this is 2 to the 1/2 power to the 16th power. So I could multiply those powers together, 1/2 times 16, and this would be 2 to the 8th, and 2 to the 8th power then is 256. Then inside here, 16 times 45, well, that's going to get me, I believe, 720. So cosine of 720 degrees plus I times the sine of 720 degrees. Now, 720, okay, if we think about on our unit circle, okay, if I go one full rotation, that would be 360 degrees. And if I go another full rotation, that would be at 720, right? So right here would be 720 degrees. So the cosine value is 1, the sine value is 0. So this would just become 256 times 1 plus I times 0. Distribute the 256, so 256 times 1 is 256. 256 times I times 0 would just be 0. So we get that 1 plus I to the 16th power is just 256. Okay, now to understand what we just did, right, we just took 1 plus I and raised that to the 16th power, right? So normally, right, if we were doing this using rectangular coordinates, I would have to write out 1 plus I times 1 plus I times 1 plus I 16 times and multiply those all out, right? That would be a horrible amount of work, right? But this gives us a nice shortcut. Okay, we just raised 1 plus I to the 16th power in just a few steps and found that that was 256. Okay, so let's do the same thing then and find z to the negative 10th power. All right, I'll put it in a different color here. So z to the negative 10th will be the square root of 2 to the negative 10th power, then times cosine of negative 10 times 45 degrees, plus I times the sine of negative 10 times 45 degrees. We can simplify, so the square root of 2 to the negative 10th power, again, this is 2 to the 1/2, so 1/2 times negative 10 would be negative 5, so 2 to the negative 5th power, or 1 over 2 to the 5th power would be 1 over 32. And then I would have cosine of negative 450 degrees plus I times the sine of negative 450 degrees. And again, we can go to the unit circle and see what these values are. And so if I'm going in the negative direction, right, negative 360 would get me all the way back to here. And then negative 450 would just be another 90 degrees. So that would get me to here. So the cosine value in this case is 0, and the sine value is negative 1. Right? So this becomes 1 over 32 times 0 plus I times negative 1. So simplifying this, 1/32 times 0 is 0, and then 1/32 times I times negative 1 would just be negative 1/32. Whoops. Negative 1/32 I. Okay, so that is the idea behind de Malvere's theorem. Right? Now, we can also find complex roots of a complex number, okay, or I should say nth roots of a complex number. So to do this, okay, we're using a similar idea, right, but slightly different. Right? If I want to find the nth root, so in our example, we're going to look at the cube roots of this complex number, 1 plus I. Right? What we're going to do is raise our R value to the 1 over n power, and then I'm going to take the cosine of theta plus 360k, okay, and our k values, we're going to start at 0 and go all the way up to n minus 1. So for example, in this one, we're going to find our cube roots, right? So I'm finding my n value would be 3, right, if I'm finding cube roots. So that means I'm going to plug in values of k of 0, 1, and 2, right, everything up to n minus 1. And so I'm going to actually find 3 different values in this case, okay, and I'm going to do theta plus 360 times k divided by n to get the angles inside here, okay? So what that's going to look like, if I want to find the 3 cube roots of 1 plus I, well, in the last example, right, we just showed that 1 plus I was the square root of 2 times cosine of 45 plus I times the sine of 45. So to find the cube roots, okay, I'm going to say that, well, I'm going to plug in 0, 1, and 2 into this formula for k. So I'm going to start with square root of 2 times, or to the power of 1 over n. So that would be to the 1/3 power times the cosine of theta, which we said is 45, plus 360 times k. So I'm plugging in 0 for k here, over n, which is 3 in this case, because finding the cube root. So whatever this value, or whatever this number is n, plus I times the sine of that same thing. 45 plus 360 times 0 divided by 3. And then we can simplify. Okay, so to simplify this, again, square root of 2 is the same as 2 to the 1/2 power. So 2 to the 1/2 to the 1/3. 1/2 times 1/3 would be 1/6 power. So I can just write that as 2 to the 1/6. And then times cosine of, well, here, 45 plus 0 divided by 3 would just be 15 degrees, plus I times the sine of 15 degrees. Okay, now for these, we can just leave our answers in polar form. So this is my first root. Okay, now I just want to go through this process again for k equals 1 and k equals 2. So here, I'll have the square root of 2 to the 1/3 power times cosine of 45 plus 360 times 1 over 3. Then plus I times the sine of that same angle. 45 plus 360 times 1 over 3. And if we simplify, this would again be 2 to the 1/6, and then times cosine. So 45 plus 360 times 1 divided by 3 is going to be 135. And we can leave our answer in polar form, just like that. So we have one more to do. Right? We need to do k equals 2. So again, square root of 2 to the 1/3 power times cosine of 45 plus 360 times 2 over 3 plus I times the sine of 45 plus 360 times 2 over 3. And if we simplify, we will have 2 to the 1/6 power times the cosine of, so I think all of this would become 255 plus I times the sine of 255. All right, so these are my 3 answers. Those are my 3 cubed roots of 1 plus I. Right? Now, if we were to ever specify that the argument or the angle should be in radians, right, we would just replace 360 in this formula with 2 pi, and we would go through the same process. Okay, so we can use de Malvere's theorem to find powers of complex numbers in polar form, or to find roots of complex numbers in polar form. All right, so that is it for this video. The final question is going to pop up asking you what questions you have.